Hello everyone! After the previous huge tutorial where we reached a new record of 25 parameters in a single shader, let's take a look at something simpler. We're going to create an effect that belongs to the category of scene transitions and resembles wiping a blackboard with a wet sponge. So let's program it. And because this is a transition, we will once again need two background images, which I'll again borrow from our game Whispers of Prague. So I'll create the usual 2D scene with all the elements that belong in it. Okay, right-clicking the scenes folder, create new scene, 2D scene, let's call it sponge wipe. Okay. And I'm dragging the usual image found in JPEG into it. The sprite 2D node was automatically created, and in the inspector I'll do the usual offset centered cancelling and opening transform and resetting position to 0, 0. And let's not forget to scroll down, open material section and create a new shader material. Then click it and create a new shader, type shader, mode canvas item, name spongewipe.gd shader, and I'll put it to the shaders shaders folder. Create and click again to open it in the shader editor. And as always, I'll delete everything from the generated code that we won't need, leaving only the fragment function, deleting vertex, deleting light, Ctrl S to save. Okay, so we'll start by creating the basic uniform parameters that are absolutely essential for this effect. As we know, for a transition between scenes, we need two images, and we already have the first one in the background of the scene. So I'll add a parameter for the target image. Uniform sampler 2D, let's call it just target, and give it the hint source color. Okay, and let's not forget to drag some actual image into that, so I'm expanding shader parameters, and into the target parameter I'll drag this chapel JPEG image. Okay. Next, we want to know at which stage of the transition we are currently are, so that later we can control the whole process from a script in our game. So let's add the progress parameter, uniform float progress with a hint range, and it starts at 0 when the progress goes from 0 to 1 with the step point 0, 1. Okay, and finally we need to define the number of horizontal sponge strokes required to cover the entire image. This will be an integer parameter, uniform int pass count with a hint range, and let's start with 4 strokes, and it goes from 1 to, let's say, 8 with a step 1, of course. Okay, so let's start writing the code, and the remaining parameters will be added as needed. As you probably noticed at the beginning of the video, the sponge wiping effect is formed by an irregular and blurred edge, which we can achieve either by using a noise texture or by calculating it through a combination of various pseudo-random number generators. I chose the second option, using the algorithm known as fractal Brownian motion, which we have already encountered many times in previous tutorials. For those who want to learn more about this algorithm, I once again recommend the excellent resource, the Book of Shaders, which is available for free on the web and linked in the video description. And as usual, we won't waste time manually rewriting the algorithm. To save time, I'll copy the relevant functions from one of the previous shaders and briefly describe them. So let me expand this window, and I'll paste the mentioned functions here. Okay, so what do we have here? The hash function returns pseudorandom numbers in their interval from 0 to 1 thanks to this fract function. And it is based on the input vector, vec2p. Sometimes we refer to it as hash12, but this time the simplified name will probably be enough. From this function, we create a variant of so-called Perlin noise, and which is handled by the value noise function. Thanks to the interpolation with the combination of mix functions, we achieve smooth transitions between edges, so the resulting noise looks nice and continuous. And finally, the FBM function combines several value noise calls with different parameters, producing a complex shape that best simulates the expected transition between images. Of course, if you don't want to copy all of this from the screen, you can get the finished shader as a part of the Godot Shader Pack product, which I also link in the video description. It is also a great way to support this channel and the creation of new tutorials. Okay, so we can move on to the fragment function, and I think I can just show to the editor again. So the fragment function, which is responsible for calculating the final color of each pixel. And this time, we are not creating a symmetrical effect either, so there is no need to shift the coordinate origin to the center. So the first line will look as simple as this. Vec2 UV equals simply UV. Our effect will consist of several horizontal bands, so we want to know their height. We'll calculate it like this. A float, let's call it n, is float of our parameter pass count, which is integer, and float band height equals 1 divided by n. Okay, you may wonder why I convert integer to float instead of simply defining the pass count parameter directly as a float. The reason is that we'll need it in both formats. Int for precisely determining which band the current pixel belongs to, and float for other calculations. The same applies to the index of the current band. We calculate it as an integer and then define a float version. So let's continue. Int, let's call it pass id x equals clamp of integer of uv.y divided by band height, and we clamp it to the range of 0 and pass count minus 1. Okay, and as I said, the float version, float pass f for float equals simply float of our pass idx. Okay, now I will add the first additional parameter, which will define the overlap between individual faces of the effect. So scrolling up to the uniform parameter section and writing this uniform float overlap with a hint range and the initial value 0.2, and this overlap again goes from 0 to 1 with the step 0.01. Okay, and we will use this parameter to calculate the so-called window, meaning the beginning and the end of the currently processed band. Scrolling back to the fragment function, and let's add this line, float, these lines, window equals 1 plus overlap times n minus 1, and let's divide everything by n. Okay, and now the start and the end. Float p start equals pass f times window minus overlap. Okay, and the end float p end is simply p start plus the window size. Okay, and because we want to know where we are inside this band relative to the overall progress value, let's define a local progress value. So it would be float local progress equals, again, we will clamp it to the range of first value. So it's progress minus p start divided by p end minus p start. So we are basically remapping one range to another, and the clamping interval is of course 0 and 1. Okay, for the next calculation, we want to know the local UV coordinates so that we can work inside a specific band. But we know that the wiping direction will alternate left and right, so half of the bands will need to flip the x coordinate, like this. So let's define vec2 local UV equals UV. But if pass ID x and 1, the logical AND, that's why we need an integer value here, because I think it doesn't work with floats, is not equal to 0, in that case, let's switch it. So local UV dot x is 1 minus, uv.x. Okay, so that completes the preparation work, and now we need to apply the actual effect according to the configured parameters. To keep the code cleaner, we'll separate this functionality into its own function, which I'll call sponge pass. It will have 4 input and 3 output parameters. So I will scroll up a little bit and insert this function just before the fragment function right here. Void sponge pass. And now, as I said, 4 input parameters, vec2 local UV, vec2 orig UV, the original UV coordinates, float local prog, which is local progress, just inside the band, and vec2 seed. This is what we'll use to increase the pseudo-random factor, and that's not all. Okay, I'll just create these curly brackets, but now we need to add the output parameters, and I'll just put them to the second row, so it's better organized. Out, float, erase mask, out, float, chalk dust, in the out, float, wet dark. I will get to them eventually when we start to work on the body of this function. Okay, so for now, let's return to the fragment function, scrolling down, where I will prepare the parameters for calling this new function. So first, we need to define a seed vector that ensures each band will have a slightly different noise pattern. I'll use randomly chosen constants in it. So vec2 seed equals vec2 of pass f times something like 3.71 and pass f times, for example, 1.93, randomly chosen. Okay, next we need definitions of the output variables that will be filled inside the sponge pass function. Let's do it here. Float, erase mask, chalk dust in wet dark. Okay, we don't need to initialize them because that will be done inside the sponge pass function. All right, and as their names suggest, they will relate to the simulation of wiping with a wet sponge, remnants of the erased chalk, wet stains, and similar effects. All of this will be configurable through parameters that we'll add soon. And now we can insert a function call finally. So let's do it here. Sponge pass with parameters. Local UV, the original one, local progress, seed, and the output parameters. Erase mask, chalk dust, and wet dark. Okay, currently the function doesn't do anything, but in the end it will fill these three variables. It will fill these three variables with new values that we'll use to determine the final pixel color. So first, we need the current pixel from both images and blend them according to the value of erase mask. So it will look like this. After the function returns new values, we'll do this. Vec4 color is a mix of two calls to the texture function. First is the target image and UV coordinates, lowercase, then texture of the original image, and again the same UV coordinates, and finally the weight factor is erase mask value. Okay, next we subtract from this value what we consider to be a wet stain. So let's subtract it, which will cause that the color will become darker. Like this, color.rgb is decreased by minus equals wet dark times erase mask. All right, and finally we add a grayscale tint according to the calculated chalk residue. Color.rgb is this time increased by plus equals chalk dust and times vec3 which is a white color. So this will result in a shade of gray. Okay, all that remains is to assign the results to the output variable color. And to be safe, we clamp the color channel values to the interval from 0 to 1. Color equals clamp of color in lowercase 0 and 1. Okay, so at this moment we still cannot see anything because the value of erase mask, this one is not defined, so Godot doesn't know what the result of this mix function would be. So let's move to the sponge pass function and finish the implementation. But I would say this is also the right moment to add the remaining uniform parameters. So let's scroll up and do that. There are 4 of them, and we'll use them to configure the appearance of the sponge, the edge of it, the erase strength, and the amount of residual chalk. So let's do it here. Uniform float sponge scale with a hint range, and initial scale would be 6, and it goes from 1 to, let's say, 20 with a step point 0.1. The second one would be called the uniform float edge softness with another hint range, and let's set the initial value to 0.06, just pretty small. Okay, and it goes from 0 to 1 with the step point 0.1. Then let's add this one, uniform float strike strengths with another hint range and the initial value 0.3. And again, it goes from 0 to 1 with the step 0.01. And finally, uniform float chalk dust amount, which gets another hint range and the initial value 0.5. And this one again from 0 to 1 with the step 0.01. Okay, and now for the function itself, let's scroll down and find it. Here it is. Sponge pass. First, we'll prepare the range for selecting the noise pattern. So float noise range equals sponge scale divided by sponge scale plus 1. Okay, next, let's define the internal coordinates, which will be slightly modified using the seed value so that the sponge pattern changes. Vec2, I'll call it NUV, equals orig UV times sponge scale and plus seed. Alright, and we shift them in the horizontal direction because the sponge does not erase evenly every line. So we add a bit of a pseudo-random factor to it. nuv.x is increased by FBM function of vec2 of orig uv dot y times sponge scale times 0.7, and the second component is seed.y plus, I think, something like 0.3. Okay, and everything is multiplied by the streak strength, I mean. Okay, and now we can calculate the final noise for the sponge. Once again, we'll do it as a mix of two different values and add some randomly chosen numbers. So float sponge noise equals mix of FBM of NUV, new coordinates, then FBM of NUV times 1.8 plus vec2 of 5.3, 2.1. Okay, and the weight factor is, for example, 0.4. All right. And then to calculate the value of erase mask, which is supposed to be our first output variable, we need to know its current position and distance. So we determine that like this. Float wipe front equals local progress times 1 plus noise range, okay, minus sponge noise times noise range. Okay, and as for the distance, dist equals local UV dot x minus wipe front. Okay, and finally we obtain the erase mask using the smooth step function and the edge softness parameter. Let's do it here. Erase mask equals smooth step of negative edge softness, positive edge softness, and applied on the distance. Wait for it. Okay, and I think we already have something here. Let's try it out. Okay, going to the inspector and let's increase the progress. Yeah, I think it's definitely working and the basic effect is finished. We can verify by changing the pass count that it actually reflects the number of predefined passes. For example, 5, 1, 2, 3, 4, 5. Yeah, definitely works. Perfect. And let's reset. Okay, so we are still missing details such as chalk dust and wet darkening. So let's finish calculating them. They aren't absolutely necessary, but they improve the results. Look. So first, I'll create a stripe for the chalk traces using a combination of two smooth step functions. Okay, let's get to the end of the sponge pass function and do that. So float dust band equals, as I said, two smooth step functions. Smooth step of negative edge softness times 3. Let's just do it a little different. 0 and dist. This is the first one, and the second one, I think I'll put it to the next line, times smooth step of positive edge softness, again 0 and dist. Okay, and the next we define a slightly different noise for this effect. Let's do it here. I'll scroll a little bit. Float chalk noise equals FBM of orig UV times sponge scale times 2.5 plus seed plus some shift solvec to, for example, 1.1 and 3.7. Okay, and before we assign the value to chalk dust, I think I'll just change the progress so we can observe the difference like this. And finally, we combine both together along with the chalk dust amount parameter. So it would be chalk dust, the output variable, equals dust band times chalk noise times chalk dust amount. Okay, and we should, yeah, can you see the difference? There is something white here, something like a white smear that that appeared, and it wasn't definitely there before. And as for the simulation of the wet area, that will be easier, and a single smooth step function will be enough. So let's add the last two lines. Float wet zone equals smooth step of, again, edge softness times 0.5, for example, 0, and let's make it symmetrical, so absolute value of dist. Okay, and I think we can make it a bit smaller, so wet dark equals wet zone times something like 0.22. Okay, and yes, I believe it's definitely there, and if we change the progress again, we should see that it looks maybe a bit more like a wet sponge right now. Okay, so I think we've achieved a satisfactory result. It's true that we could occasionally observe transitions between the individual bands that weren't perfectly clean, but that all depends on the parameter settings or on improving the pseudorandom number functions. And I would say that if we apply this transition quickly enough, the resulting effect will be ideal. Thank you very much for watching. This time we managed to keep the number of parameters low. There were only 8, which had a positive effect on the length of the video. I hope you'll find this shader useful and will definitely return to a similar topic again sometime in the future. Until then, take care, good luck with your projects, and I'll see you in the next video.